Please, the stage is yours.
Yeah, okay. Yeah, thank you for inviting me to this workshop. Unfortunately, I cannot be present. And basically the talk that I prepared for today is called Virtual Humans from Appearance to Behavior. And basically, I will talk about some of our recent works on that in that direction. And you will see that there's also lots of common points with what Julian was describing. So in our lab, we have roughly 3 areas of research. So first, one is human appearance. This basically entails building models of the human, how humans look. So this means modeling the geometry and also modeling the appearance, like texture. We're also interested in general models of shape and scene representations. So here we're investigating representations of scenes that are amenable for learning, that allow then re-rendering of scenes and manipulation of scenes. And we're also interested in like human behavior. And this is going to be the topic of this talk exclusively. And this entails basically capturing fine-grained human interactions and then learning models capable of synthesizing this sort of interactions. So since the beginning of civilization, we spent our lives interacting and perceiving other humans. And that's a society we live in where humans play a central role. So the human body and human interaction has been depicted multiple times throughout art and history. So now with the new modern tools of AI, it's perhaps not surprising that one of the grand goals of AI is to build agents that not only look, but also eventually behave like real humans. And this entails creating agents that can navigate the 3D scene and can basically interact with the 3D scene and act upon the 3D scene. So as Julian was pointing, like data is key, and for modeling human interaction is the same data is key. And the first step to model this, to be able to synthesize this type of fine-grained interactions, is to be able to capture real humans interacting in the open 3D world. And this was one of the goals of our paper from last year, which we call like human positioning system, which we presented at CVPR last year. So basically the goal here was to not only capture the human motion, as you can see here, but also be able to register where the human is within a 3D map of the environment. So here we assume that we know we have a 3D reconstruction of the environment, and we want to reconstruct the human motion coherently with the surrounding 3D environment in a way that is realistic. And the problem is that if we look at the systems that were available until then, they mostly are based on, for capturing fine-grained interactions, they are mostly based on external cameras. And the problem with external cameras is that they place a limit on the recording volume. So the recording volumes are typically confined and very small. And it also places typically a limit on the duration of the recordings. Typically, these recordings last for a few seconds, at most minutes, but you cannot really capture interactions like, for example, multiple activities that might happen within a building or in an open space. So we're interested in capturing long-term motion registered with the 3D world around us and on large scenes. So basically what the restriction that we had here is that we wanted to capture this without using external cameras, because otherwise it's not possible to satisfy these requirements. And so basically we want to capture using wearable sensors, and these are inertial measurement units placed at the human body, as well as a head-mounted camera that is looking out, like emulating the field of view of the real person. So the research question is like, how can we capture human motion and register it with the 3D scenes without using external cameras? And well, the first potential solution is to use inertial sensors because they don't require external cameras. But the problem is that if you've played with inertial sensors, you will know that they drift over time, and they do not take the environment into consideration when they are recording the motion. So this means that after a few seconds or no, a few seconds of tracking, like the person will be not registered with the scene, and then the person will be, flying through the air or crossing walls and not really like you will not be able to capture really a motion that is coherent with a 3D scene. So because we have the head-mounted camera, one idea might be to combine visual localization from the head-mounted camera together with IMU pose estimation. So here on the left, you see like a split screen where on the left, you see the real camera. This is what the person is seeing when the person is walking. And on the right, you see the synthetic rendering of the scan as seen from the camera pose estimated using visual localization. So if you have a good localization, then these two should perfectly align. And this sort of joint optimization leads to better results. So the person is not traversing walls like before, but it can still like penetrate the ground or can fly above the ground. And basically the results are not very realistic. And the reason is that visual localization itself is very challenging and you can have many errors. And it's like sometimes not that accurate. So it's difficult to obtain like very good results with just combining visual localization and IMUs. So what do? We are basically jointly optimizing the information coming from visual localization, from IMUs, as well as from the geometrical constraints coming from the environment. What are these geometric constraints? For example, we know the person cannot penetrate the ground. We know the person cannot fly above the ground. We know that when the person is walking and hits the ground, like the feet should stay static. And so basically, these are the sort of constraints that we can impose during tracking. We can also impose that the person should follow, the orientation of the person should follow the trajectory of the person. So basically, we integrate these three sources of information in a joint optimization framework in order to obtain human motion that is registered with within the 3D scene. So these are the sort of results that we can obtain using this, we can call it hybrid tracker. So here we can record where the person is within the scene because we are integrating the visual localization. And perhaps the most interesting thing of these results is that we can for the first time record human motion interacting in large 3D scenes. And this was until that point, to my knowledge, not possible. And I think this is, in terms of data, very interesting because it opens doors to building agents that can perform motion based on what they are seeing. And then basically like, build these agents that can behave a little bit more like real humans. So using this method, we recorded a wide variety of interactions. So here, I should emphasize, we're not only interested in the trajectory of the human, but we're also interested in fine-grained interactions, like, for example, typing on a keyboard or, interacting with a coffee machine or dragging objects and things that involve like the full body and not only like the trajectory. So here we're showing two persons being jointly tracked and localized within the same scene. So we see that they are coherent to each other, which is good. There is an obvious thing that is missing here, which is the object, and I'm going to talk about this later. So at this point, we could not track changes in the environment. We could only track the humans, which is an obvious limitation. And here I want to emphasize that we could record human motion on scenes that were more than 1,000 square meters. So we can record some types of interactions that would not be possible with external cameras. So this is what we can see here. We see a human for every time snapshot. So we can see the behavior of the human in space-time. We can also record interactions in different rooms in a single recording session. So basically we can record a person like preparing coffee and then going back to the room and then maybe like then going and giving a lecture and so on. So we were interested in like this sort of like behavior that happens when we're basically, like our daily activities throughout the day. So this is part of the same recording. And here we wanted to illustrate that the method does not drift over time because basically it uses the visual localization So it can always rely on this visual localization to not lose track of where the person is within the environment. So this data is available for research purposes. And if you're interested in these topics, I encourage you to have a look at it. And yeah, you can always contact us if you have some doubts about the data or about the method itself. So there is one obvious limitation, and I was mentioning this before, and it's the fact that we can track the human, but we could not track the changes in the scene. So you can see here that the person is opening the door, but the door is not being opened. And by the way, this hole that you see on the left is because when we 3D scanned the scene, the door was open, so you cannot reconstruct what was occluded by the door. So don't be confused by this. So now the question is like, okay, using the same input data, like a 3D scan of a person and also like the wearable sensors and just a single egocentric view of the human object interaction, as you can see here. So you see that there's a lot of occlusions and there's like, it's very difficult to know what's happening because like the object is very close. The question is like, can we recover not only the human motion, but also the motion of the object, as you can see here. So that's a question that we are investigating, and this is ongoing work, and we have some progress in this direction, but know that this is a very exploratory research direction because there's many challenges. So for example, you could think, okay, what I'm going to do is I'm going to register first, I'm going to localize the object relative to the human, and then I'm going to localize the human relative to the scene so I can solve everything together. Now, the problem with this approach is that, first of all, human localization is very often not accurate. I mentioned this before, because the camera is basically sometimes blurry or doesn't have enough features to match against the 3D scan, and it's very difficult to localize. Also, the object, when we're interacting with the object is sometimes barely visible. So we barely see the object. Or, for example, we have like something similar to the aperture problem here, where the person is moving the object, but we don't see the object moving because basically it's moving relative to the person, the object is not moving. So it's very difficult to know exactly how the object is moving if we are not having some higher level reasoning about human object interaction. So this approach of just localizing the object and then localizing the human within the scene will not be sufficient. And in this talk, I don't have time to explain like our proposed solution, but the basic idea is to reason about the human object interaction in a way that we enforce contacts between the human and the object during the interaction. And we also parameterize the object motion. For example, a door can only move along a hinge joint, and a very heavy chair can only be dragged along the floor. And then basically using these constraints and how the human moves during the interaction, we can figure out how the object is moving. So what does this mean? Before we had this HPS method that cannot reason about the object. And now we can basically recover as well the human and the object jointly. So this is quite interesting because you could imagine like some VR applications in which you're basically, you're opening a physical door, but this opens also a virtual door to like a new environment and so on. So it will probably, apart from the goal of learning agents that interact with humans, this can have also immediate applications in VR and AR. So as I was saying, it's very important to reason about contacts when we're dealing with fine-grained interactions, and we basically are also dealing with contacts here, and we enforce that the human is in contact with the object during the interaction. Okay, so this is like our work on capturing with egocentric sensors, but and basically some VR AR applications require wearables devices, and egocentric capture is better for these unconstrained volumes where the persons are interacting in open spaces across multiple rooms. But if we're interested in smaller objects and confined scenes and like close range interactions, it makes still a lot of sense to use the more classical external camera-based capture methods. And this is what we worked on. Like, this is work that we'll present at CBPR this year, which is called Behave, which is essentially a data set and a method for tracking human-object interactions. So the goal here is to track the human, the object, and their contacts in 3D using a multi-view RGBD setup. So when we look at traditional capture setups, we find marker-based methods, which are high quality. The data you get there is really good, but they're very expensive and they are limited in recording volume. They require like placing lots of cameras in a fixed room. And it's not easy to scale the recording locations because these systems are not movable. And basically the markers also get often occluded during human object interaction. So if we're capturing things like interactions on a table or things like that, it would be not ideal. Then we have IMU-based capture methods, which are easy to scale and they don't have restrictions on recording volume. And our recent work even allows us to capture this jointly with a 3D scene, which is good. But if we look at the close range interactions, they are not very, very accurate. So if you looked at the person, when I was showing this video of the person interacting with the coffee machine, you could see that the hands are not really matching and sometimes it's a little bit inaccurate. So we want something in between. We want something that is easy to use and we can place in many different recording locations in order to scale this data capture process. So what is Behave? Behave is a data set including multi-view RGBD frames. And we have the 3D human model, which is basically simple. And the 3D human and 3D object fits to the data. And the data set includes as well like 3D annotations of the human object interactions. So more specifically, it includes 4 calibrated Kinects, 8 subjects, including 5 males and 3 females, 5 different locations, and 20 daily use objects and interactions. So with each object, you will find that there's, so the objects are, for example, like boxes, chairs, tables, and monitors, and so on. And the type of interactions are quite varied for every object. So we record sitting, lifting, dragging, pulling, and pushing, and so on. So this is an example of like the type of interactions that we captured. And yeah, I mean, this is the largest data set of with this accurate human object annotations in 3D. And I'll explain next how we obtain these annotations. We also have interactions with backpacks, or for example, like interacting with a table, and the person is carrying the table with in many different ways with different types of contacts. And as you can imagine, tracking these interactions is extremely challenging because you have lots of occlusions, and that makes it very, very challenging. So, okay, how did we actually obtain these annotations? So this is based on essentially optimization and a sophisticated pipeline using state-of-the-art detection, but even state-of-the-art detection of objects and humans fail sometimes. So we run things through mechanical Turk to fix like when the detector was making mistakes. We also fit the simple model. The simple model is a parametric model of how humans look. So we optimize a simple model to fit the 2D detections in the images. And we additionally annotate like key points on the object such that the object pose is accurate. So so Julian was pointing at this, and we face the same problem. Like this capturing process is costly and it's time consuming and it's tedious. But sometimes when you're starting a project, you need to do this like sort of hard work in order to start to get things running, right? And now we're very happy that we have this data, and we're hopeful that this will be very useful for the community. But of course, the question is like, okay, this is a semi-automatic method. How can we automatize this so that we can scale and capture data much more in a much more streamlined fashion? So this is where the Behave method comes into play. which is basically a way to automatize this sophisticated optimization pipeline that I just described. So taking the input point cloud, which is coming from the Kinects, we assume a segmented human and object. And essentially, we train a neural network that predicts like the distance field of the object, the distance field of the human, as well as correspondences from this input point cloud to this human model. In a way that we call this the neural reconstruction, in a way that then we can feed the parametric model of the human and the object to these neural reconstructions in order to obtain the best of both worlds, like the learning-based mechanisms and the more optimization-based mechanisms. So in more detail, how does this work? So what we actually predict is we're based on neural fields here. So basically for every point in space pi, we predict the distance to the body model. This is annotated as UIH, okay? And now once we have these predictions from a neural network, which are trained with using the behave dataset, we want that the distance from the PI to the actual body model that we're fitting, M is our body model shown here, that we're fitting to the point cloud. We want that the distance from this body model to PI matches the actual distance predicted by the neural network UI. That's why we have this distance here minus this distance, and we want to minimize this, discrepancy, basically. In addition to the human body, we want the object mesh template to fit with a neural reconstruction. This means that the vertices of the object should be at the zero level set of the neural reconstruction. And this can be enforced with this objective function here, which is summing over object vertices. And we want that the distance field at these vertices is zero. That's why we minimize the sum of distances. uj0, this is the distance field of the object. And we also have a chamfer distance between the object and between the template O and the input object point cloud. I was mentioning before that it's very important to model contacts when you're dealing with human object interactions. And that's why we have a term that is specific for the contacts here. So basically we have an indicator function denoted as 1CJ, which takes value 1 when the distance field for the object and the human are less than 2 centimeters at the same time. So in this case, we assume that there's a contact, and therefore we impose that the object point Vj matches the model point M evaluated at the correspondence point Cj predicted by the network. Yeah, so for more details, like I refer to the paper, but this is the basic idea. You have a neural reconstruction, which reasons about humans and objects, and then we feed the parametric models of the human and the object to these neural reconstructions. Let me see this, yeah. So these are the results that we can obtain with this method. And what is interesting is that the quality of the results is very much, it's pretty much the same as the quality we were obtaining with this sophisticated semi-automatic pipeline, which is really nice because it means that now we can automatize this capture process for novel motions and subjects. So we have another example here of a person interacting with a ball. And notice here that we assume that the ball is rigid, so we cannot track these non-rigid deformations. So surprisingly, there were not many approaches available to compare against. And so here we compare against a method that is called PHOSA, which is a single image reconstruction method. Notice that this comparison is not fully fair because this method uses a single image, whereas we use 4 depth images. But this is just to illustrate that this method is based on handcrafted rules and optimization. And this is to demonstrate that if you don't jointly reason about the human and object during the learning process, it's going to be very difficult to obtain accurate results that generalize. So the conclusions are that the behave dataset is the largest full-body human object dataset featuring interactions in natural environments. With the behave method, now we can track humans, objects, and the contacts between them. And the code and data is available at the following website. And if you're working on this area, I really encourage you to have a look at it. And if you have doubts, yeah, just contact us. Okay, lastly, I want to show like a more fair comparison to the state of the art on single image reconstruction. And this is, I want to present the method that is called CHORE, which is contact, human, and object reconstruction from single RGB images. And essentially, this is a single image reconstruction method that has been trained using the behave data set and that jointly reconstructs the human and the object from a single image and improves the state of the art significantly. So basically, from single images, the challenges are quite different and the problem is much more difficult. The first challenge is that you have a lot of depth ambiguity. You don't know how far the person is. And in this case, you don't know how far the person is from the object. You have sometimes heavy occlusions, so the person is completely occluding the object, making the reconstruction really difficult. And essentially, like prior work like PHOSA addresses these limitations by like these challenges by handcrafting the rules. So for example, it would say that we interact with a racket by grabbing the racket from the handle, or we would sit on a bench in a particular manner. Now, this sort of like resolves some problems, but you can already imagine that this introduces a lot of problems because heuristics essentially do not scale, because we can interact with the same object in many different ways. For example, with a chair, we can sit on it, we can lean, we can move it, we can displace it, and it's very difficult to handcraft all these possible things that we can do with each object. It's basically not scalable. So in CHORE, we're interested in learning this, addressing this basically these challenges by learning learning the common interactions between humans and objects. So what we do is we predict from a single image what we call a neural interaction field that predicts the surface of the object of the human, as well as the correspondences from these neural reconstructions and the templates, and also correspondences from the object and the human. There's also very important tricks that are required in order to learn a neural reconstruction from single images, which unfortunately I don't have time to explain here, but if you're interested, let me know, because these tricks are also core to the method and basically they are essential to make the method work. So at a high level, what we're doing is we're jointly reconstructing the human and the object with a neural interaction field, and then we are fitting like, yeah, we were basically learning the typical spatial arrangements of humans and objects. And the benefits are quite significant compared to this method that is based on optimization and handcrafting the rules. So on the behave data set, we can reduce the error metric, which is the chamfer distance, by over 50%. So both on the human and the object reconstruction. So the improvements are significant. And let me show you also some qualitative results. So you can observe that basically, because we have learned these typical configurations of humans and objects, we can reconstruct the humans and the objects better than this model that handcrafts the rules. So here we show a sequence where we're not doing tracking, but we do single frame reconstruction, and we can show that our method is still coherent over time. So notice that this method that handcrafts the rules sometimes works, but many times it also like produces very incoherent results. So this method, like the good news is that it not only works on the behave test set, but it also works on other data sets like these previously. Oh, now it broke. Can you tell me how we're doing on time? Just so I know, because I have to reinitiate this.
Yes, you still have maybe a few minutes before the coffee break, because then the coffee break will follow.
Okay, good. So sure you're all eager for coffee. So let me finish this. Sorry about that. It's not the first time that happens. Somehow it keeps breaking my PowerPoint. Okay, so I believe I was here. Yeah, so on this other data set, we are also obtaining better reconstruction, especially like at the contact locations, and also for images on the wild. Here we don't have like any way to metrically compare, but we can compare using user studies. And also here the improvements. Oh no, man, this is really. Sorry about that. Okay, so for this, oh, this is like really annoying. Okay, let me see what I can do. Maybe I'll jump these animations. This is auto-saved. Let me try something. Sorry about this.
It's okay. Maybe we skip one slide and continue from the next one if it doesn't work.
That's what I will do, but I'm afraid that it's breaking for different slides. I don't know. Let me just try one thing. Oh, okay. Okay, so basically the conclusion here, or the take-home message here, I'm just afraid that this will break again, so I don't want to show more results. I have more results for this, but I will show only this one. Basically, the conclusion is that also for images in the wild, this generalizes, but I want to point out this is a significant improvement over the state of the art, but it's clear that this is only the first steps because it fails for many other images, and also it's restricted to a set of objects. So this is clear that, you know, these are the first steps towards modeling human and human object interactions from single images. It's an exciting problem, a new research area, but there's still lots of work to be done, right? Because there's when there's heavy occlusions or when the objects have not seen during training, then the method would fail. Okay, so just to conclude, no, I don't want to postpone the coffee break any longer. So basically, capturing and synthesizing human behavior is extremely challenging, and we're only at the very beginning. But that's basically, there's an opportunity for lots of exciting research happening in this area. Long-range interactions require egocentric capture algorithms, and I showed one example, which is the human positioning system. I was showing that when you deal with egocentric data, capturing, especially tracking the object motion is very challenging because it's not very visible on the camera. And then for short-range human object interaction, I've shown Behave, which is the largest data set of human object interaction, including data from multi-view images and depth as well, with accurate 3D human and 3D object reconstructions. And for reconstruction from images, I've shown that one can learn these interaction neural fields, which can be learned to represent humans and objects. And then you can fit parametric models to them. And in the future, there's lots of work to be done. So we will investigate, in particular, algorithms that capture and synthesize more complex behavior, including sequences of atomic actions, and also more complex environments and more complex images in the wild. And I want to thank my students and collaborators. And also I want to say thanks to the funding agencies. And now if there's questions, I'll be happy to answer. Thank you.
Thank you for the presentation. Do we have some questions from the audience maybe?
So I may have a question actually here, Luigi. Simply, you concluded saying that you go towards handling more complex scenarios, environment. One question that I have related to this is the fact if you plan to, or if you work already considering more than one single human, right? Like you have more complex scenes where actually there are human-human interactions. Maybe there is also some human-robot interactions, like physical interactions. So if you have done already something in this direction, or you are planning to.
We did some work on capturing multiple humans from single images, but there it was just the humans, not the objects. What we haven't done yet is to capture multiple humans interacting with objects, and this will make it really challenging because there's many more opportunities for occlusions, making the problem even harder, but also making the problem more interesting. So yeah, it's definitely, we were eager to tackle, but we haven't yet.
Thanks. One question is coming here from you.
Thank you, Gerard, for a great talk. This is Alex. I had a question about the required resolution to understand this interaction. Like, for instance, in body pose, we extract 16 body joints sometimes, or 133. Do you have any comment on what you think is a good level?
Yeah, so I think from the resolutions from you're asking about the behave data set, or you're asking about the images in the wild?
I guess my intuition is like for a small object interaction, you might want to also extract the figures, right? Like detailed pose and figures and so on.
Yeah, excellent question. So this, right now we've focused here on full body human object interaction, but of course, the hands are super important. We're addressing this, we're dividing a little bit this problem. So there's people working on full body interaction, and there's people working on hand object interaction. And we're hoping to put this, these research lines together eventually. But so far we're addressing it a bit different, separately. But definitely, like, you need some way of recording these things simultaneously. One way might be from the head mounted camera. You might record like the hands at a higher resolution, and as well like use external cameras for recording the full body. Yeah, these are things that we're thinking about right now. Yes.
Thank you so much.
So from the room, no more questions, I think.
Okay, if there are no more questions, then maybe this is a good time to conclude this first section of our workshop. And I hope that in the next 20 minutes, we all are able to find a local source of coffee. And then in 20 minutes, we meet for the second round of presentations.
Thank you.